Hey everyone, I'm Nick, and in this episode of This Week in Architecture, we're going to be talking about a paper that was recently published at ISCA 2019, right? So this was just from a few weeks ago. Right? And ISCA stands for the International Symposium on Computer Architecture. It's one of the top conferences in the computer architecture field. Right, so the title of this paper is SCU, a GPU stream compaction unit for graph processing. Right? And it comes from Barcelona Tech. So let's go ahead and made a quick presentation that we'll briefly go over, right? So, first of all, overview of the paper. So graph algorithms are highly parallel, but they suffer from memory divergence, right? So we've got some applications like matrix multiplication, which follow very set and predetermined paths during execution that we know ahead of time. But other applications like graph algorithms, right? The control flow is data dependent, right? So we don't exactly know, how we're going to touch memory until we actually start dereferencing things, right? So matrix multiplication will access, very nice contiguous elements. Graphs may be all over the place, right? So, to an extent, we can remedy this, right? And we do this algorithmically through something called stream compaction, right? So in the case of a graph algorithm, a lot of times we will do some kind of exploration. So we'll expand out, right? And then we have this stream compaction process where we basically, after we expand out, we contract, right? So we have, say two different kernels, one where we add nodes to some frontier, and then the second step where we contract that down. But GPUs are really kind of unsuitable for this kind of purpose. Right, and the reason why is because GPUs like things that are contiguous, right? So we have things like memory coalescing that makes use of the fact that, or that encourages us to access contiguous chunks of memory. So if we have sparse data that's kind of spread out, this isn't that, it's not something that runs very well on GPUs. And if we look at some, typical graph applications that get run on GPUs, so things like BFS, SSSP, and PageRank, right? We see that a large portion of time, over 50% in the case of BFS, gets spent on the stream compaction process, right? And this darker bar represents the rest of graph processing, right? And the two GPUs being compared here are an embedded one, which is this Tegra, this TX1, and then a GTX 980, right? So what is this paper trying to shoot for, right? So it's a programmable stream compaction unit called SCU, and it efficiently gathers active nodes and edges into a compacted array in memory. Right, so let's go over some background, right? So GPU algorithms gather nodes from an array or from a graph into a compacted array. Right, so compacted data sets lead to better memory access patterns, and there's a number of ways we can do this. So one of the most intuitive ways, right, and one of the most classic ways of doing this is through a prefix sum, which is kind of shown here, right? And so we see we've got, some kind of array that's sparse, right? So these x's represent elements that we don't care about. So we'd like to kind of squish this down, right? So we end up, just creating kind of a bit mask, right? So 1 represents an active element and 0 represents an inactive element. And we do a prefix sum, which is basically just kind of an aggregate sum, right? So we count up over time the number of elements, right? So at the very beginning, 0, right? And then we add 1, we get 1. We don't add anything here, so it stays at 1. Then we add another 1, we go to 2, etc., all the way up to the very end, we have 8. Right, and then this allows us to pretty easily shuffle everything down into a compacted format. Now, another thing we can do is this thing using a population count method, right? So this is a bit nicer because it allows us to avoid doing a prefix sum. Basically, what we do is it's a process of doing it forces you to support a couple things, such as in the case of a GPU being able to every single thread in a warp being able to access the same bit mask, and also being able to get basically a count from each of those from each thread in a warp based upon which threads should be active, right, or which threads have active nodes like this. And the actual process is fairly easy, but this kind of gets the point. This is what we're trying to do, this end result here, right? But again, this is bad on GPUs, right? Because A, it's sparse, right? So we don't have lots of things that are close together. And then B, overall, we've got a bad compute to memory access ratio. So, we've got data we're accessing, but we're not doing much with it after we access it. GPUs have a lot of ALUs. They're mainly optimized for doing a lot of compute, right? And this has a very bad compute to memory access ratio. So let's talk a little bit about graphs and algorithms, just as kind of a refresher. So we've got some reference graph that can be represented in some representation, right? So this is CSR, which is compressed sparse row, I believe. So we've got, say, nodes, and then we have adjacency offsets, right? So these adjacency offsets, they point to where we should be looking inside of these weights. So in the case of, say, A is connected to B, C, and D, right? And so we see that A starts at 0, right? And we see 2, 3, 1 are the 3 weights for A, right? And so B starts at index 3 now, right? So it's just a compressed way of representing sparse data like this, right? And then we've got some graph exploration. So here we've got, say, for BFS, right? So what happens, we've got a node frontier. So say we're at B, C, and D. And what we'll end up doing is we'll go ahead and add every single node that we find at the edge frontier, right? So B is connected to E and F, so we'll add those 2 nodes. C is connected to just F, so we'll add F. And D is connected to C and G, so we'll add C and G, right, to the edge frontier, right? So this is kind of this expansion phase, and then we go to a contraction phase. You'll notice it will have 2 Fs here, and this is an artifact of the fact that these things are happening currently, right? So each thread is going to be mapped to, say, a different node, right? And these nodes will all be accessing their adjacency lists at the exact same time, right? So there's no real way for us to prevent that with the baseline hardware. And likewise, you've got something similar with SSSP, right? So you have your node frontier, say B, C, and D, and then you've got your edge weight frontier, and then based upon some threshold, right? The threshold's 3. You've got a far pile, and then you've got the I+1 node frontier. Now, as far as the stream compaction unit, so this is the kind of block diagram architecture of what they're proposing here. They break things down into basically 5 different functions. So they have a bit mask constructor, right? And this requires a reference value and comparison operation, right? So how are you actually going to create your bit mask? A unit for data compaction. So this accesses sparse data and filters out unwanted elements. So like we showed with kind of the prefix sum thing, we want to get rid of some elements and store things consecutively. Then we have access compaction. So we want to access a sparse index vector and filter out unwanted elements as well. Replication compaction. So this basically extends data compaction, as well as access expansion compaction, right? And so this makes more sense here, right? So we've got our bit mask constructor. So we've got some comparison that we're doing, right? And so we take A, B, and C, and then we end up with a bit mask on the other side. So here, the 0 and the second element are both valid, and then we've got an X around the first element that's invalid, right? So this is, a dedicated unit for, doing this operation. Then we have data compaction. So say we take this bit mask, and then we've got source data. So we turn it into a compacted data array, right? So here, the 0th element and the second element we want to keep, but we want to get rid of the first. So we take our source data and use the bit mask to compress it down into this compacted data here. So we get rid of B, and we just have an array with A, C, and whatever other elements are valid. Then we have, say, access compaction. So if we want to access some part of the source data, right, based upon, say, a bit mask, right? So we'll go ahead and access it, but we'll make sure that when we're accessing it, we're accessing the compacted data, right? So we'll have, say, some index, right? So we're accessing the 0th element and the second element, right? And that corresponds to index 1 and index 2, right? So we'll end up getting elements B and C, and we'll move those to a compacted data array. There's replication compaction, which is similar, except this count basically says how many of what element are we taking, right? So here it says 2B, so we've got B replicated or replicated once here, so we've got B and B, and then we have just 1 for C, right? And then there's access expansion compaction. So we say we have a count, right? So we've got 2 starting at index 0, right? And this basically says, okay, I want A and B, right? So this isn't replication, this is just access. So how many elements starting at index 0? 2, which is both A and B. And then over here, it's 1 element starting at index 2, right? So C, so only C is getting read out, right? But it gets read out in a compacted way, so we're still compacting things together. Now, let's make it more friendly for GPUs, right? So the 2 things we want to do is, of course, we want to filter out duplicated elements, right? So that's where they add this filtering grouping block. And then you want to reorder compacted data for memory coalescing, right? So just because you have, say pointers, they are all accessing that are consecutive. When you start accessing what those pointers are pointing to, right? Those may not be adjacent in memory or on the same cache line, but there may be some locality between accesses, right? So, different sets of accesses. You might find some locality in terms of, well, from this request, 2 things are, or 2 nodes are from this cache line, and 2 nodes are from the same cache line and another request, right? So you mash them together, right? And you just read out both of those in one request from the same cache line. So the main idea is we're grouping nodes that are on the same cache line. So as far as the evaluation goes, they use an in-house simulator. They use GPU Watch, which is part of GPUSim, or GPUSim for power and area measurements. They also have a Verilog implementation for area and energy of the SCU itself, right? And so, so here they look at, of course, here's the baseline for the GPU they use, so the GTX 980, and also the mobile one, the Tegra X1. Right, and so they run this on, they only run it on 3 apps, but they run it on a variety of different networks or different graph data sets. So one of the interesting things about graph applications is that a lot of time, your performance characteristics of your graph application, they'll be pretty strongly influenced by whatever your input data is, right? So a lot of their control flow is going to be data dependent, right? So just as it's important to have, a variety of applications for, applications that have very data dependent control flow, it's important to have a variety of inputs, right? So as far as results go, you see that in terms of normalized energy, right? So you've got the GPU energy versus the SCU energy. You see the total normalized energy, you get these great reductions for the GTX 980 and TX1 for BFS and SSSP. A little less so for PageRank over here, but still pretty good savings overall. And you see the averages are good. Now for the execution time, right? So you see about 20% or a little over 20% on average improvement in execution for the GTX 980, and about almost about 60%, right? Of course, PageRank doing a little bit worse. And then you've got a couple other things here. So, how do you compare the baseline SCU that we showed back here, right? And then here we've got the stream compaction unit that's been modified to have this filter grouping and coalescing unit, right? So this doesn't, this won't do anything for PageRank, but it'll work for BFS and SSSP. So hence why there's only 2 apps here. So you see that, compared to the baseline SCU or basic SCU implementation, the speed up is 1.4x, the improved speed up, and the energy reduction is about 12x, right, for the GTX 980 on BFS. Not quite as good on the TX1, but still about 4x, 6x for speed up and energy. And for SSSP, similar style results, right? Then you have the memory system, of course. So, how do we get these performance benefits and how do we get this reduction in power? So dynamic energy is going to reduce because, we're running, it's faster, right, overall. Secondly, we're having fewer sparse accesses and fewer accesses overall. So we see that we've got an improvement in memory coalescing. So, we're having to read out fewer cache lines, right? So we see that, across these different graphs for SSSP, we get a pretty good increased percentage in memory coalescing, right? And over here, you've got your memory bandwidth utilization, and you see that your GPU versus your SCU, right? You see that, you know, the 980, it decreases bandwidth a little bit. TX1, it increases, and this is, I would guess this is mainly because you're getting, you know, better coalescing, but for the GTX 980, because you've got better coalescing, you know, you might not get quite as good of bandwidth, or your bandwidth utilization might go down, because you've got more, you know, coalesced axes, so fewer axes overall. But these are kind of up and down across here. So some final thoughts on the paper. So it's a very clear paper, right? It does a great job constructing these ideas with fairly impressive results, especially in terms of energy. And it complements the existing architecture, right? So now this actually sits alongside the SMs. It's not actually integrated in with the cores or anything. It kind of just sits alongside the SMs connected to the interconnect. So some criticisms, it's of course, you know, it seemed like it has a little bit of a limited evaluation exploration. One thing it does do, this is a programmable unit inside of the actual GPU itself, meaning that it's going to change the programming model, which, you know, that always has a cost associated to it, because now you don't need to just know how to program a GPU, you need to know how to program a stream compaction unit as well, or program for a stream compaction unit. So it's not invisible to the programmer. The other thing is, you know, it is a separate accelerator sitting alongside the GPU, which makes me kind of think of, you know, well, you know, if this is such, you know, a problem, or this gets, you know, such benefit, not being really integrated with anything other than the GPU memory system, right? You know, would this be better suited for, you know, being its own accelerator? And there's been other works that have looked at, you know, dedicated graph accelerators. And so some other thoughts is, you know, things to improve for GPUs is going to be this kind of scatter gather support. Now, whether this is in the form of dedicated accelerators sitting alongside the SMs in the GPUs, or better support within the cores themselves in the memory system for scatter gather operations, that's a possibility, as well as, you know, a better understanding of divergence and workload balancing, right? So, you know, how do you know, what does the future look like in terms of, you know, graph applications running on GPUs if this is such a problem? But that's going to go ahead and do it for this video. All right, let's go ahead and fix this typo right here. Model. Right, so this was SCU from ISCA 2019. Right, and you see, if you actually look at the paper itself, you see you've got all these, that's where all these pictures come from. So this is the overall Tegra architecture, including the SCU. So you see you've got your SMs, and then you've got your stream compaction unit sitting along the side connected to the interconnect, which connects to the L2 cache. You also have, you know, some examples over here. So what does BFS kind of look like with, you know, using the SCU, PageRank, and SSSP, right? As well as some, you know, of course, more detailed explanation into, you know, the evaluation methodology, additional operations with the enhanced SCU, so implementations with both the baseline and the enhanced, as well as some, of course, information about the evaluation and explaining these things. But that's going to go ahead and do it for this episode of This Week in Architecture. Feel free to check out any of the other, you know, videos in this series, or any of the other series I have on programming. So, you know, related to GPUs, I've got one on GPU micro benchmarking, as well as this one on CUDA programming. So if we just look at the CUDA programming one real quick, we've got examples on, you know, if you're just new to things, some basics on environment setup, vector addition, matrix multiplication, and some optimizations such as tiled in shared memory, some optimizations on sum reduction. So here we actually went through 4 or 5 different optimizations, and then we've got some other things on, say, convolution and histograms as well, and using the CUDA libraries. That's going to do it for today. I'm Nick from Coffee Before Arch, and I hope you have a nice day.